Welcome back. Today we're going to talk about discrete random variables, and this is the context that we're going to use, the probability distribution. And as we talked about before with the probability distribution, what we have is a chart, and it outlines X, which are the events, and then below is the probability of X. And as you'll remember, and as you'll recall, to be a valid probability model, it had to be everything, all the probabilities added up to 1, so 100%, and they each had to be between 0 and 1. Well, when we do a probability distribution, what we're looking at is a discrete random variable. Okay? And it takes a fixed number of values with gaps between values. What are we going to do with this? Well, one of the things that we can do is we can make a histogram. And our histogram on the vertical axis is going to have our probabilities. And on the bottom, it's going to have our potential values of X. And it'll look something like this. You'll have like 1, 2, 3, 4, and then our bars will come up in this way, kind of like that. The other thing that we're looking at is this concept of what's called a mean, or our expected value. And the formula for our expected value looks like this. Mu of X, so the mean of X is equal to the sum of all of our X values times their probability. So you take, you're given X value times your probability of X, you add that to the product, 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 and it's going to equal your mean or your expected value. And really what this is it's more of a weighted average because it takes into account how often each of those outcomes or those X's came out. Let's look at an example. Remember, a good way to do a check your understanding is for me to read the prompt or you to read the prompt, pause the video, try it on your own, and then unpause to watch the explanation and see if you got the answer right and make any corrections that you need to. I'm going to go ahead and keep going, but this would be a good time to pause if you want to try to do it on your own. Home Alone is a series of American Christmas family comedy films created by John Hughes. There are 5 Home Alone movies. Below is a probability distribution of the number of Home Alone movies watched by a very large sample of high school students. So up here, this would be our X, and it's 0 through 5. Down here is the probability of each one of those events happening. Assuming that this is a valid probability model, all of these should be equal to 1 altogether, and they should each be between 0 and 1. So as you can see, as we go down the line here, we've got our different probabilities. We're obviously missing 1. Our first question is, write the event. The student has seen 3 Home Alone movies using probability notation. Then find this probability. So that would be the probability that X is equal to 3 because X is our number of Home Alone movies watched. And so X equals 3 would be the probability that a student has watched exactly 3. To find it, that's our one that's missing here. To find that, we take all of our possibilities and we subtract everything that we have. So I'll just add up all of my probabilities here. And when I subtract them from 1, I get 0.08. So that's what goes in here. Here's this. 0.08. Okay, now it's a valid probability model. I have all of my probabilities listed for each of the given X values. They want us to explain in words what P of X greater than 3 means. What is this probability? Well, if this is the number of movies watched, this would be the probability that a student has watched more than 3 movies. This would be the probability that a randomly selected student has watched at least or 3 or more Home Alone movies. Okay, so at least 3 or more Home Alone movies. Well, the probability of X being greater than or equal to 3 is equal to the probability of 3 plus the probability of 4 plus the probability of 5, which is equal to 0.08 plus 0.02 plus 0.01, which is equal to 0.11. So 11% probability that a student has watched at least 3 of the Home Alone movies. Let's make a histogram of this probability distribution. Up the side here is going to go our probabilities. And so if our probabilities go up the side there, I'm actually going to move this over just a little bit, give myself some space. My probabilities, I see that my biggest one is 0.42, so I really need to go just up to 0.4, because I don't necessarily need to go all the way to 100 because I'm measuring each of the individual probabilities on this scale here. And here's my 0, 1, 2, 3, 4, and 5. That's all my movies there. Because down here is number of movies watched. So 0 movies watched would be 0.15, so I'm going to put that here. This one is 0.42, so I'm going to connect my dot up here. And then for 2, it is 0.32, so I'll be down a little bit. 3 is 0.08, so just below 1. 4 is 0.02, so very small. 0.5 is here. Okay, now they want us to describe its shape. Well, I notice that I've kind of got this guy here. And as we remember, skew follows the tail, so it is skewed right with a single peak at 1. So most people have watched 1 of the Home Alone films. So now we're going to calculate the expected value of X, and that is our U of X. What does that actually mean? So that would mean if I randomly pluck a student out of this group and I don't know how many they've watched, this would be the number that I would expect them to have watched based on all of the probabilities that I've already collected. And it's going to take into account every single probability listed. So it's going to be my probability that they watched 0. It's kind of a weighted average. It is a weighted average. 0.42 plus 2 times 0.32 plus 3 times 0.08 plus 2 times 0.02 plus 1 times plus 4 times 0.02 plus 5 times 0.01. And when I do that math, that's me taking into account the heaviness or how often each of the given outcomes came up. I get 1.43. So when I interpret this, this would be in many student selections at random, the average number of Home Alone movies they have seen is about 1.43. Okay, so what did I say before? You pluck a student out and they've seen 1.43 movies. Well, think about that. That doesn't really make sense. And so the average student having seen 1.43 movies comes from the fact that we have this big collection that may have different amounts that they've seen, right? So even in this group that we pulled out up here, how does a person see 1.43 movies? They don't. But one person, so pulling out one person, seeing 1.43 movies, we would expect them to have seen more than one but less than two. Well, yes, but that's because it's the average of all the many, many, many that we would have asked there, okay? So that's the concept of expected value, guys. Thanks for watching, and we will see you next time.